In this video, we're going to talk about some properties of matrices and their determinants. So we're going to start with Theorem 3.5. And these are really just to make some computations a little bit easier. If we can recognize these properties, then finding the determinant may not be as difficult in some cases. So Theorem 3.5 says if A and B are square matrices of order n, that means that each matrix is an n by n matrix. Then the determinant of the product AB is equal to the product of the determinants. So determinant A times determinant B. So let's look at an example. Let's say we have two 3 by 3 matrices. And we need to know what is the determinant of AB. Well, this is a good one where we could use that property that guarantees us the determinant of AB is equal to determinant of A times determinant of B. So if we were to do it this way, that's going to take some work, right? We would have to multiply those matrices first, and then we would have to find the determinant. Whereas the way this is set up, B is a diagonal matrix, so that determinant is super easy since it's just the product of the entries down the main diagonal. And then A would have an easy determinant to find as well, because if you notice, we have 2 zeros along that bottom row. So let's use that shortcut here. So the determinant of B, like we said, is just going to be the entries down that main diagonal. We talked about that in a previous video. And if we were to multiply those together, we're going to get a negative 6. So now let's find the determinant of A. And that one's going to take just a little bit of work. So I'm going to do an expansion along the third row. And the reason I would choose that is because I'm going to have some zeros here. So we're going to have 0 times negative 1 to a power times this product. So that's going to be 0. And I'll write that out so you can see that. That's in the third row, first column. And then we would have that 1 times negative 1 to the 3 plus 2. And then plus 0 times negative 1 to the 3 plus 3 times this matrix determinant. So 0 times anything is 0. We could have left out writing those zeros. I just wanted to show you where that was coming from. So now let's compute this. So we have 1 times negative 1 to the 5th, which will be 1 times a negative 1, which will be a negative, times that determinant. So we're going to have a negative 1 minus 1, which is a negative of negative 2, which gives us a positive 2 for that. So the determinant of A is 2, so we should get a negative 12 for that. So if we were to do it the other way, just for fun, suppose we didn't want to use the property. You can see how that property is going to save us some work. To find that determinant, we would first have to find the product of A and B. So if we were to find that product, we get that. And then we would have to go back and find the determinant of that. So I'm going to do an expansion along that third row again. So we're going to have some zeros, which are going to be nice. This time I'm not writing those zeros. So the only thing we're going to have to worry about is 2 times negative 1. That's in the third row, second column, times this. 2 times negative 1 to the fifth is going to be a negative 2. Times that. So we're going to have 3 minus negative 3, which is negative 2 times 6, which is a negative 12. So you're going to get the same answer either way. The point is that this guy took a little bit more work, in my opinion, because I had to do a multiplication first and then I had to find a determinant. Whereas the other way up here, because I had a matrix that was super nice here, because it was a diagonal matrix, that determinant is easy to find. So that product, I call it like a product rule for determinants, was actually a little bit easier to compute. We didn't have to do any extra work. We really just had to find the determinant of this B matrix, which was easy because it was just a diagonal multiplication. And then we had to do a little work to find the determinant of A. But we didn't have to find a product of AB. So sometimes these are going to be helpful, and sometimes, it may be just as broad as it is long, computing the product. So it just depends on the problem. So let's look at the next property. Theorem 3.6 says the determinant of a scalar multiple of a matrix. If A is a square matrix of order n, so A is, again, an n by n matrix, and C is some scalar, then the determinant of C times A is going to be equal to C to the nth times the determinant of A. Okay, and keep in mind what n is. N is going to be the order of the matrix. So let's look at that one. So suppose we had the matrix 5, 15, 10, and negative 20. So this is a 2 by 2. It wouldn't be terrible to work this one out by hand. The numbers are going to get large, though. That's where this property would really come in handy, is when you have really large numbers and you notice they have some multiple in common. So notice every entry here has a 5 in common. So that's the same thing as 5 times the matrix, 1, 3, 2, negative 4. Well, finding the determinant of this guy is going to be super easy, right? So the determinant of that matrix would be negative 4 minus 6, which is negative 10. So then our determinant, I'll call this matrix A, of A would be 5 squared, because this is an order 2 matrix, this is 2 by 2, times the determinant of that smaller matrix. So we're going to have 25 times a negative 10, which is a negative 250. So if we did it the long way, well, maybe not long way, maybe it's more like the hard way because of the bigger numbers, we could multiply that out. 5 times negative 20 is negative 100 minus 15 times 10 is 150. So that would be a negative 250. So you're going to get the same answer either way. The property is really just showing you, computations can be made a little bit easier using some of these properties. So I want to show that for a 2 by 2, a generic 2 by 2, that the determinant of CA is equal to C to the n times the determinant of A. So we're going to let A be a 2 by 2 matrix. And we're going to define A to look like this. So I think you'll be able to see it come out. And we could do the same thing for a 3 by 3 and a 4 by 4, but those proofs are going to get a little tedious. But I think you'll be able to see it with a 2 by 2 pretty easily. So then the determinant of A would be A11, A12, just kidding, A22, minus A12, A21. It's AD minus BC. So then if we were to look at CA, the scalar C let's define that up here, times matrix A would look like this: CA11, CA12, CA21, and CA22. So now let's look at the determinant of this guy. We're going to have CA11 times CA22, which is C squared A11, A22, minus, and then we would have CA12 times CA21, which is C squared A12 times A21. And notice both of those terms have a C squared in common, so we could factor that out. And this guy is the determinant of our matrix A. So notice that 2 there. That happened because we had 2 rows. So every row in that matrix was multiplied by C. That's your definition of scalar multiplication. So if we had something that was order 3, then to find that determinant, we would have C raised to the 3rd power. So let's look at one of those. So suppose we had something like this. And we wanted the determinant of that matrix. So if we were to do this the long way, those numbers are going to get pretty big. Especially if we're doing this maybe without a calculator. So we can make the computations a little bit easier by realizing that every row is multiplied by 5. So we could rewrite this in terms of scalar multiplication. So keep in mind, this guy's a 3 by 3 matrix. So if we want to find that determinant, then this property says it would be the same thing as finding the determinant of 5 cubed times the determinant of this reduced matrix. So let's find the determinant. Let's do some side work here. And this is going to be a little bit easier to deal with because the numbers are smaller. So let's find the determinant of that guy. So I'm going to use that shortcut method on this one. You could do an expansion along any row or any column. Since there's no zeros, there's nothing that really stands out to me as to I should do this column or this row. So I'm just going to use that shortcut. So we're going to multiply 72 plus 60 plus 84 minus 270 plus 224 plus 6. So order of operations, 72 plus 60 plus 84 is 216. 270 plus 224 plus 16. Just kidding, it's a plus 6. 500. So 216 minus 500 is going to be negative 284. So then our final answer is going to be 5 cubed times negative 284. And that's going to be a super big number. Oh, technically it's super small because of the negative. So we got negative 35,500. So that's certainly easier to compute than just going for finding that one, because those numbers are just going to get gigantic. So there's another property to kind of help reduce some of the computational load. Theorem 3.7, that's one we talked about before. How do you know if a matrix is invertible? Well, a matrix is invertible if and only if the determinant's not 0. So anytime you get the determinant as 0, then that means that that matrix will never have an inverse. But if it's not 0, then you have a non-singular matrix. You have something that you can invert. And what's nice about invertible matrices is that we can solve systems in a couple of ways. We could say AX is equal to B. So if we wanted to solve the system using AX equals B notation, then we can multiply by A inverse on the left on both sides of the equation. And that's going to give us the identity times X, which is X. So then we can solve systems using that kind of notation. So if we have a matrix that's invertible, we know the determinant's not 0, but is there a relationship between the determinant of A and the determinant of A inverse? And it turns out that there is a relationship, and that's what that next theorem talks about. If A is an invertible n by n matrix, then the determinant of A inverse is equal to 1 over the determinant of A. So let's look at an example of that. Now, I want to talk a little bit about notation here. I think this is a good place to do it. So we're saying we're using the format DET, which means determinant. But another way to write that is using those absolute value looking lines. This means the same thing as writing it out in word form. So the determinant of A inverse is equal to 1 over the determinant of A. So just keep in mind that the notation can change. This is certainly easier to write mathematically than having to write words out. So be aware of the notation. So let's look at an example. Let's say we have the matrix 1, negative 2, 2, 2. And we want to know what is the determinant of A inverse. Well, we don't have the inverse of this, but we can find the determinant of A. So the determinant of A in this case is going to be 2 minus negative 4, which is 6. So that means the determinant of A inverse must be 1 over the determinant of A, which must be 1 over 6. So we can find that determinant without ever finding the inverse. Now, another thing we know is that because that determinant of A was something other than 0, then this is a non-singular matrix. And what that means is it guarantees this guy is invertible. So there's an inverse that exists here. Now, if we were to do this the long way, you could see how this is going to take some work. So let me do that in a different color. our first step would be to figure out what is that inverse. Well, the inverse is 1 over AD minus BC times the matrix. We switch A and D. We negate B and C. So we have 1 over 6 times the matrix. 2, 2, negative 2, 1. So that would be 2 over 6, which is a third. 2 over 6 is a third. Negative 2 over 6 is negative 1/3. And 1 times 1 over 6 is 1 over 6. So there's A inverse. Now to find the determinant, it would be AD minus BC. So we have 1 over 18 plus 1 over 9, which is 1 over 18 plus 2 over 18, which is 3 over 18, which is 1/6. So you can see how this way definitely would take a lot more work than using that property that relates the determinant of A with its inverse. So now we can build even more conditions for a non-singular matrix. And we started this a section or two ago. We said if A is an n by n matrix, then all of these statements are actually going to be equivalent statements. If A is invertible, then that means that AX equals B has a unique solution for every n by 1 column matrix of B. So, and we talked about this just a second ago. We could take this and solve by finding that inverse. So then X is going to be equal to whatever A inverse times B is. There's always going to be a unique solution for that as long as A is invertible. Unique means that we're going to get just one number for each X, each Y, or in 3 dimensions, each X, Y, Z. 3 says AX equals 0. So now we're talking about a homogeneous system of equations. And we're saying that there's only one solution for that. We know that from that second condition. And since there's only one solution, then that means that has to be the trivial solution, which means that X has to be 0, Y has to be 0, Z has to be 0 if it's in 3 dimensions. Or X1 equals X2 all the way up to Xn, which is equal to 0. What all of this also means is that that matrix A is also row equivalent to I. So we could do all of these elementary row operations and we will eventually reduce this down to an identity matrix. And if we can do that, then that means that A can be written as a product of elementary matrices. And we saw that in chapter 2. Where each row operation equated to an elementary matrix. So if we were to multiply all of those row operations together, which resulted from those elementary matrices, then we would get this A matrix back. And all of this also means that the determinant of A is not equal to 0. So we're building this list as we're going through this course, and we'll add a few more things to this as we go through. And then the last thing in this section talks about the determinant and the transpose. So if you remember what a transpose does is it inverts the rows and columns. And it turns out that the determinant of A is equal to the determinant of A transpose. So I want to go through an example and I want to explain why that works. So let's say we have a matrix. Let's just use 1, 2, 3, 4. And I'm going to use a 2 by 2. It doesn't matter if we use a 3 by 3 or anything. So the determinant of A in this case would be 4 minus 6, which is a negative 2. if we were to find the determinant of A transpose, A transpose flips the rows and columns. So we're still going to have 4 minus 6 here, which is still going to be a negative 2. Now, if we were to change this to a 3 by 3, and we were to find the determinant of this, and I'm going to show it with row expansion. Well, so let's expand along the first row here. I'm going to call this matrix A, by the way. So we're going to have 1 times negative 1 to the 1 plus 1 times 5, 6, 8, 9 plus 2 times negative 1 to the 1 plus 2 times 4, 6, 7, 9 plus 3 times negative 1 to the 1 plus 3 times 4, 5, 7, 8. So if we were to expand along the first row, that's what we would have. So we're going to have 1 times negative 1 squared, which is a positive 1, times the determinant of this matrix, plus 2 times negative 1 cubed, which will be a negative 2, times the determinant of this matrix, plus 3 times the negative 1 to the 4th, which is a positive 3, times the determinant of this matrix. So 45 minus 6 times 8 is 48, minus 2, 36 minus 42, plus 3, 32 minus 35. So negative 3 minus 2 minus 6 plus 3 times negative 3. So you can see how that's going to give us 0. So we know the determinant is 0. Now I want to show you what happens with A transpose, and I'm going to do that in a different color. So we chose to expand along the first row. We could have expanded along any row or any column, and we would still get 0. If we were to look at A transpose, well, A transpose just inverts the rows and columns. So that first column is going to be 1, 2, 3. The second column is going to be 4, 5, 6. And that last column is going to be 7, 8, 9. Now remember, I can choose any row or any column to expand along. Expanding, if I were to expand this along that first column, that would be identical to expanding along the first row for A, which is going to produce the same stuff. So that's why that determinant has to be the same. So that determinant for A transpose, because I can expand along, I can choose to expand along that first column, which would be the same as expanding along the first row in the original, I'm still going to get the same thing. I'm still going to get 0. So that's kind of cool. So these properties are to help you cut some computations. This section is really just did you know that you could do this type section with some theorems and some other things, equivalent conditions that kind of help us wrap our mind a little bit more about all of these properties and how they work.